Across the ruins of the ancient world, they stand like forgotten guardians. Weathered stone towers rise above collapsed cities, their masonry defiant against 2,000 years of wind, frost, and earthquake. In southern France, a circular stone basin crowns a hillside above Nîmes. In Turkey, square brick towers loom over Ephesus and Aspendos. In the Jordanian desert, cut stone chambers perch atop the cliffs of Petra. Travelers who stumble upon them ask the same startled question. Why would anyone build a tower for water on high ground when no pipes seem to reach it? The stone is here, but the plumbing is gone. To the untrained eye, the sequence looks impossible, even reversed, as though these structures were raised before any network could have justified them. That impression has bred a modern legend. Videos circulate claiming these towers predate the water systems they served, that they were monuments of unknown purpose, or relics of a lost technology we cannot explain. The mystery feels irresistible. A massive stone reservoir, elevated deliberately, connected to nothing visible, standing alone against the sky. But engineering, not magic, put these towers on their perches. Every one of them obeyed a single ruthless logic, the logic of gravity. Roman engineers, Nabatean masons, and Byzantine builders all understood that water stored high becomes water that moves with force. An elevated tank of 30,000 liters could feed fountains, baths, and homes downhill without a single pump, driven only by the weight of the water itself. The towers were never empty riddles. They were the beating hearts of vast hydraulic machines, positioned exactly where physics demanded. What vanished were the fragile arteries. The lead and clay conduits that carried water outward and then decayed, were robbed, or were buried beneath centuries of soil. The durable stone survived. The delicate pipes did not. And so the illusion was born, a tower without a network, a cause without its effect. To understand these sentinels, we must first confront the myth head-on and ask why durable stone so reliably outlives everything it was built to serve. The answer begins with a single, deceptive absence. The claim spreads fast online. These towers, it insists, were built before any pipes existed, so they cannot have been water infrastructure at all. The argument sounds compelling because it rests on something real. When investigators excavate around an ancient tower, they frequently find no intact pipes leading to or from it. The stone rises, but the plumbing is absent. Surely, the reasoning goes, the tower must have come first. This is a textbook case of survivorship bias, the same logical trap that fools us everywhere. We judge the past by what remains, not by what was originally there. Consider the materials. Roman distribution pipes were made of lead, cast into sheets, and rolled into cylinders roughly 20 to 30 centimeters wide. Other conduits were fired clay, joined with mortar. Both were extraordinarily valuable and extraordinarily fragile. Lead could be melted and recast into coins, weights, bullets, or roofing. A single kilometer of lead piping represented tons of reusable metal, an irresistible prize for anyone after the empire's collapse. Clay pipes shattered under frost, root pressure, and the slow crush of accumulating earth. Now compare the tower itself. Built of quarried limestone or fired brick, weighing hundreds of tons, useless to melt and awkward to demolish, it simply endured. Nobody carried off a 30-ton stone basin. Nobody could recast masonry into currency. So across 15 centuries, the pipes were stripped, corroded, and buried, while the stone stood untouched. What we excavate today is not the original system, it is the wreckage after the salvage. The absence of pipes proves only that pipes were the first thing to disappear, exactly as we would predict for the most valuable, most fragile components. To argue the tower predates its network is like finding a lighthouse without its lamp and concluding the tower was built before light was invented. The evidence for connection is still there if you know where to look, in the channels, sluices, and mounting scars carved into the stone. But before we read those marks, we must understand why builders wanted height so desperately in the first place. The answer is pure physics, and it turns falling water into force. Water does not climb on its own. Before electric pumps, engineers had exactly one reliable way to move it through a city: gravity. And gravity rewards height. This is the principle of head pressure, and it governed every ancient water system ever built. The rule is simple and unforgiving. For every meter of vertical drop, water gains roughly 0.1 atmospheres of pressure, about 10 kilopascals. A tank raised 10 meters above the streets delivers water with the force to push it through pipes, up into fountains, and across distances no flat channel could manage. Elevation is not decoration. Elevation is stored energy, waiting to be released downhill. The Romans mastered this with staggering precision. Their aqueducts descended at gradients as gentle as 1 part in several thousand, sometimes dropping only a few centimeters per kilometer. Too steep and the water would race and erode the channel. Too shallow and it would stall and stagnate. But when that carefully graded flow finally reached the city, engineers needed a way to convert the aqueduct's long, slow descent into usable pressure at many points at once. The answer was to lift the water into an elevated tank. From that height, the stored volume pressed downward through distribution pipes with predictable force. Open a valve at a bathhouse, and water surged. Open a spout at a public fountain, and it flowed continuously, day and night, because the tank above never ran dry as long as the aqueduct fed it. This is why builders hauled tons of stone up hillsides and raised towers where none seemed necessary. The height was the entire point. A reservoir on high ground could serve neighborhoods below without a single moving part, no pump, no engine, nothing but the weight of water obeying physics. It could also branch a single incoming channel into many outgoing pipes, each carrying its measured share downhill under pressure. That branching function had a name and a form: a circular stone basin bored with outlets, standing at the terminus of one of the greatest aqueducts ever built. To see the principle made physical, we travel to the Roman city of Nemesis and the Castellum that fed it. In the French city of Nîmes, ancient Nemesis, a remarkable structure survives at the end of a 50-kilometer aqueduct. It is the Castellum Divisorium, the distribution basin, and it is one of the finest examples of Roman hydraulic engineering left on Earth. The water reached it after an extraordinary journey. Rising from the Fontaine Dieu spring near Uzes, the aqueduct wound across the countryside, crossing the Garden River atop the Pont du Gard, a 3-tiered bridge 49 meters high, before finally arriving at the edge of the city. There the channel emptied into the Castellum, a shallow circular basin roughly 5.5 meters across and about 1 meter deep, cut into stone and set on elevated ground above the streets. Look closely at the basin's wall, and the purpose becomes undeniable. Bored through the stone are 10 circular openings, each about 40 centimeters in diameter, arranged around the lower rim. Into these fitted 10 lead pipes, and through them the single incoming flow was divided and dispatched across the city, to public fountains, to bathhouses, to private homes, and to industrial workshops. 1 aqueduct entered. 10 arteries departed. The basin was the branching point where a river became a distribution network. The design also managed volume and pressure. As water pooled in the circular reservoir, it lost velocity and settled, and its stored height pressed evenly into every outlet. Engineers could regulate the shares, prioritizing public supply while letting overflow drain away. Some scholars believe sluice mechanisms allowed operators to cut off individual pipes during shortages, protecting essential fountains first. Today the lead pipes are gone, stripped and melted centuries ago. Only the empty bores remain, 10 dark circles staring out of the stone. And this is precisely how the myth takes root. A visitor sees the basin and its holes but no pipes, and imagines a mysterious structure without purpose. Yet the holes themselves are the proof. Their diameter, spacing, and downhill orientation record exactly where the vanished pipes ran. The Castellum is a machine missing its limbs, its function written permanently in stone. That same stone reveals another vital job the elevated basins performed, one that protected the entire system. They cleaned the water before it ever reached a home. Aqueduct water was never clean when it arrived. Along its journey of dozens of kilometers, it gathered sand, silt, grit, organic debris, and dissolved minerals. Left unchecked, this sediment would have clogged pipes, fouled fountains, and coated every channel with abrasive sludge. The elevated tank solved this problem through nothing more than patience and physics. When fast-moving aqueduct water flowed into a broad, deep reservoir, it slowed dramatically. As velocity dropped, the water could no longer carry its heavier particles. Sand and grit sank to the bottom of the basin, while cleaner water rose toward the outlet pipes set higher on the walls. This is the principle of the settling tank, and the Romans understood it intimately. Many distribution structures included a dedicated sedimentation basin, sometimes called a piscina limaria, positioned before the water entered the city network. At sites like the aqueducts feeding Rome itself, these settling chambers were built into the line, deliberately widening and deepening the flow so debris would drop out. Workers could then periodically drain the basin and shovel out the accumulated muck, a routine maintenance task that kept the whole system alive. The engineering payoff was enormous. Clean water meant fountains that ran clear, baths that stayed usable, and drinking supplies far safer than a muddy river. But the deeper benefit was durability. Every gram of sediment removed at the tank was a gram that never scoured the interior of a lead or clay pipe downstream. Grit acts like sandpaper, wearing away pipe walls and building blockages that burst joints under pressure. By stripping out solids at elevation, the settling basins protected the fragile arteries and extended their working life by years. Placing the tank high thus served two purposes at once. Height gave the water pressure to travel, and the wide, calm basin gave sediment time to fall. One structure delivered force and clarity together, the elegant core of ancient hydraulic design. Yet the pipes those basins protected so carefully were still doomed. Made of soft lead and brittle clay, they were the weakest link in the entire chain, and when the empires that maintained them faltered, those vulnerable arteries were the first things to vanish from the record entirely. Stand inside a Roman castellum today, and you will find a puzzle of empty holes. 10 circular sockets ring the basin at Nîmes, each once gripping a lead pipe as thick as a man's arm. The sockets remain. The pipes are gone. To understand why, follow the metal itself. Roman plumbers cast their fistulae from lead sheets, rolled around a wooden core, then soldered the seam. A single distribution main could weigh hundreds of kilograms. Lead melts at just 327 degrees Celsius, low enough for a modest fire to reduce a pipe to a puddle. When the Western Empire fractured after 476, that soft, valuable metal became irresistible. Medieval scavengers pried pipes from trenches and melted them for roofing, coffins, ammunition, and church bells. A buried aqueduct pipe was, quite literally, a vein of money. Clay pipes suffered a different fate. Fired terracotta segments, sealed with lime mortar, cracked under freezing water, root pressure, and earthquakes. Once a single joint failed, the line drained, silted, and collapsed. Farmers plowed the shattered ceramic into their fields, mistaking it for common rubble. Even the great lead sheets of Roman Bath and the pipes beneath Pompeii show gouges where later hands stripped them. Corrosion finished what theft began. Lead exposed to certain waters forms a crust that flakes away over centuries. Iron fittings rusted to nothing. Wooden board pipes used in northern provinces rotted within decades of abandonment. Burial did the rest. Cities rose on their own rubble, lifting streets 2, 3, 4 meters above the Roman grade. The delicate network sank into darkness, while the reservoir, anchored on bedrock, kept its head above the accumulating soil. This is the asymmetry that fools the modern eye. Distribution required kilometers of vulnerable, portable, meltable pipe. Storage required one massive block of stone or brick-faced concrete, too heavy to steal, too solid to crack, too plain to bother demolishing. Time is a filter, and it kept the crude and discarded the refined. The arteries vanished, the heart remained, and that same asymmetry repeats far beyond Italy, in deserts and on hills where empires never spoke Latin at all, wherever gravity and stone conspired to preserve the tank. Cross the Bosphorus and descend beneath Istanbul, and gravity's logic reappears in the dark. The Basilica Cistern, completed under Justinian around 532, holds 80,000 cubic meters of water beneath 336 columns. It is not a tower but its inverse, a sunken reservoir fed by the Valens aqueduct, storing water from forests 120 kilometers away. Yet the principle is identical. Capture the flow at height, hold it, release it under control. The aqueduct's arches still stride across the city. The fragile lead siphons that once threaded its valleys are almost entirely gone. Travel south to Petra, and the Nabateans reveal the same mastery in rose-colored rock. By the 1st century BCE, they carved channels along cliff faces, feeding ceramic pipes cut to precise diameters that slowed water and reduced turbulence. Settling basins, positioned high in the Sick, dropped sediment before the flow reached the city. In a desert receiving barely 150 millimeters of rain a year, elevation and storage were survival itself. The stone channels endure. The pipes, once sealed with careful joints, survive only in fragments displayed in museum cases. In Anatolia, the pattern repeats across 1,000 years. At Aspendos, a Roman aqueduct built in the 2nd century used two towering pressure structures, still standing over 30 meters high, to force water across a valley through an inverted siphon. These were not decorative follies. They were engineering necessities, points where the water dove into pipe and climbed again, and where the head had to be broken to protect the line. The pipes that ran between them are dust. The pressure towers remain, misread by tourists as gateways or monuments. From Byzantine columns to Nabatean cliffs to Anatolian siphons, no magic connects these places, only physics. Different empires, different centuries, different faiths, all answering the same question: how do you move water without a pump? The answer was always height. And the survivors were always the heaviest, plainest, most immovable pieces of the system. To read them correctly, we must learn the grammar of stone, the sluices and channels and pressure marks that betray a structure's true purpose, before myth rushes in to fill the silence. An archaeologist approaching a lone stone tank does not ask what it looks like. She asks what it did. The evidence is written in the fabric itself, if you know the vocabulary. The first word is the channel. Where water entered, a stone trough or ceramic conduit meets the wall at a fixed height, often with a lip worn smooth by decades of flow. At Nîmes, the incoming channel from the Pont du Gard aligns precisely with the basin rim, proving the tank received, not stored in isolation. The second word is the sluice. Look for slots cut into stone where wooden or bronze gates once slid, controlling how much water passed to each outlet. These grooves cannot be decorative. Their placement matches the hydraulic logic of division. The third word is the mark of pressure. Lead pipes leave stains, calcium deposits, and mineral crusts, where water sat under load. Sockets show wear on their lower edges, where the weight of a full pipe dragged downward. Overflow channels, cut at the maximum safe level, reveal that engineers expected the tank to fill and needed somewhere for excess to escape. Together, these features form a signature no mystery can imitate, a structure built before any water network would show none of them. No aligned inlet, no calibrated outlets, no sediment layer settled on the floor. Yet the ancient mystery claim ignores everyone. It photographs the bare exterior, strips away the plumbing that theft already removed, and declares the emptiness proof of impossible antiquity. This is the misreading, treating an incomplete survivor as a complete original. Correct reading restores the missing pieces logically. The 10 sockets demand 10 pipes. The settling floor demands incoming grit. The overflow demands a source above. Each absence points to what was stolen, not to what never existed. Archaeology does not need magic, because the stones testify plainly, sluice by sluice, stain by stain. Assemble that testimony, and a single verdict emerges, hard as the masonry that carries it. These were working parts of vast hydraulic machines, and their endurance was never a mystery, but a lesson, one the evidence has been waiting to deliver in stone. Gather the evidence and the case closes without a single unanswered question. The towers were never mysteries, they were machines, and every stone confirms it. We began with weathered sentinels that seemed to stand before their purpose existed, and we found the opposite. They stood because their purpose required them to be built strong. Elevation was the whole design. Raise water 30 meters, and you store energy no pump could match, energy that drove flow through every fountain, bath, and household in a Roman city. The Castellum at Nimes split one aqueduct into 10 controlled lines, its sockets still counting the pipes that fed 20,000 people. Height also cleansed the supply, letting sediment sink in elevated basins so that grit settled in stone rather than clogging the network below. Function explains the perch. Survival explains the emptiness. Lead melting at 327 degrees became coins and roofing. Clay cracked and was plowed under. Iron rusted. Wood rotted. And rising cities buried the fragile arteries meters deep. What remained was the one component, too heavy to steal, too solid to crack, too plain to demolish, the reservoir itself. Time filtered the system, discarding the refined and preserving the crude. That same filter operated everywhere, from Justinian's cisterns beneath Istanbul, to the Nabatean channels of Petra, to the pressure towers of Aspendos. Different empires reached the identical answer because gravity offers no alternatives. And when tourists mistake a stripped tank for an impossible relic, the stones themselves correct them, through aligned inlets, worn sluices, mineral stains, and overflow channels that reveal a working purpose. The mystery was only ever a misreading, an incomplete survivor mistaken for a complete original. Restore the missing pipes, and the impossibility dissolves into engineering. So the verdict stands, carried in mortar and dressed stone across 2,000 years. These structures did not predate their water networks. They anchored them, divided them, cleaned them and pressurized them, and then they endured while everything more delicate around them was melted, robbed, corroded, and buried. The evidence points in one direction only, plain and unshakable as the masonry that delivers it. The towers outlive their pipes.